All right. I guess it's recording, all right. So, okay, for better or worse, we can try and see if anyone wants to watch such a thing at home. Okay. So I said that we will introduce zero knowledge proofs. So the idea of a zero knowledge proof is that it is a two-party protocol. There is a prover and verifier. P is for prover, V is for verifier. Where V runs on some what we call statement X, which might or might not be in some language L. Okay, and think of L as some hard language. So, for example, X is a statement where it includes a commitment to a transaction on a blockchain, and you don't know, is it a commitment to a valid transaction or not? It's a commitment to something that somebody claims is a transaction. It's a valid transaction. No one can tell if it is or if it's not, except of the party that created this commitment. Think of a commitment is like in the homework, in the last problem, there is this nice tool, which is that one of the parties can commit to something, and then they decommit, meaning they open the commitment. So in this case, the other counterparty can verify that they really open this commitment. But the commitment has the property that it's like an encryption. Given a commitment, you don't know anything about what was committed. You need to wait for an opening. So you can think of commitment as an encryption. So in other applications, X can encrypt whatever other things. Like, for example, X can encrypt your backup keys. X is an encryption of your backup keys. You don't know whether it's encrypted correctly. The person who performs the encryption does, but no one can tell because the encryption is secure. So X is the ciphertext, right? You cannot know what's whether that ciphertext encrypts the valid statement or not. And P has what we call a witness. W, which allows for efficient verification that X is in language N. So, for example, X is an encryption. X is a public key, the public key of a CA, of a certificate authority, from last lecture, right? The public key of a certification authority, and a ciphertext. The witness is the secret key and randomness, such that everybody can verify that first the ciphertext encrypts the secret key under the public key of the CA using randomness R. So this is the public key encryption. This is the public key of a certification of the CA. This is the randomness use encryption, and this is the plain text, meaning that this ciphertext is an encryption of the secret key. this is what we would call an escrow application. You have encrypted your secret key under some trusted CA public key. And second, this secret key has some meaning. A secret key public key pair is a valid public key pair. So how can I use it? This is my public key. And let's say I'm supposed to escrow the corresponding secret key under some trusted authority public key. Well, I escrow, meaning I encrypt my secret key under the escrow agency public key. But no one knows whether I have done so or not. Maybe the ciphertext is just a bunch of garbage, right? If encryption is secure, no one can tell. But I do have a witness. If I had revealed this witness, then everybody would be able to verify, right? Because this is an efficient verification, and this is an efficient verification. You know, in general, if a blockchain, say, security asks me, okay, I'm supposed to put something on the transaction chain that is that commits me to some actions that I'm going to do in the future. But like, you know, for example, I put up I put up that I will pay whatever amount, you know, if somebody does this and that. Well, how do anybody know that I have that amount in my bank, right? Well, perhaps I encrypt all the proofs that are needed to verify that I have the money in the bank, that transaction is not an empty promise, right? But who verifies? How can this be verified? So that's an example where the prover, he knows the statement that is being proven, like that this is a valid, for example, a valid escrow of some meaningful stuff, secret key corresponding to a public key under some public key of some authority. And he has the witness to this. Can he, in some interaction, convince the verifier who does this statement, but does not have the witnesses? So he's unable to verify on its own, right? Because like in this example, you know, I've got two public keys and a ciphertext. I have no idea what the ciphertext encrypts. But yet, we want this guy to output 1 if X is in the language. Like for example, this is the language of proper. So what's the language here? The language is, you know, implicitly here defined. The language of triples, public key of an agency and a ciphertext, such that there exists a W, such that these two properties are satisfied, right? And a W is SK out. Right, so I didn't spell out what's the language, but the language is it's a set of all tuples of that form. And the question is X, a tuple that a verifier has, of that form or not? And 0 if X is not. So, you know, a trivial way to for a prover to convince the verifier that the statement is true is from a solution send W to the verifier. Right? If the prover just sent his witness to the verifier, then the verifier could locally verify all these equations. Okay. So Well, but that's a trivial solution, which basically means that the only way I can prove to you that something is correct is to reveal all my secrets straight away. Right? So yeah, I reveal, for example, my own secret key here. So in order to prove to you that I have escrowed the secret key that corresponds to my public key, I have to just reveal to you my secret key. Okay? So that's clearly no good. Or in this blockchain application, in order to convince you that I have, all the money in the bank, I just have to open all my accounts and show you exactly right, rather than somehow commit to it and be able to prove to you without revealing my secrets. Zero knowledge of a proof system means that essentially, in some very intuitive way, this view of the interaction with the prover who has the witness leaks no information about the witness, except that it exists. So, I mean, what I want to leak to you is that I do have that witness, that the witness exists, that the statement is true. But that's all. So it leaks nothing else. We have seen in cryptography, how to state such properties, like how to state that a ciphertext leaks no information about the plain text. Well, how did we state it? We said that like for any M0 and M1, ciphertext which is an encryption of M0 is indistinguishable from a ciphertext which is an encryption of M1. So perhaps we could do the same here, like for any two witnesses, W0 and W1, interaction with the prover that has W0 is indistinguishable from the prover that has W1. That is indeed sometimes a useful notion called witness indistinguishability, but it's not super useful here because what if the secret key is unique given a public key, right? So it's indeed every public key crypto system you have seen, which is Diffie-Hellman and RSA. The secret key is a deterministic function of the public key. So in Ergamal, right, this is the G to the X and this is the X. So there are not two X's which are discrete blocks of the key. So the fact that if I have a valid witness W0, then you cannot distinguish me from a run where I have a valid witness W1 is meaningless because there is only one witness anyway. Okay, so it wouldn't capture. So instead, formally, or more formally, a little more formally, very first view of interaction with the prover is computationally indistinguishable from the first view of an interaction with efficient algorithm called simulator. Sim, who holds only X as its input. So pictorially, the verifier will interact with some prover. That's what happens in the real world. Like there is some prover, he has a valid witness, he has a secret key, and so on. You know, there is some statement. Public key of authority ciphertext. There is a prover who created this ciphertext and who holds the secret key, and he did it correctly. So he does hold this witness. And when he interacts with the verifier to convince him that the statement is true, you know, that's the real world execution. No problem. No problem. But there is we can call it ideal world, where the verifier instead looks to an efficient algorithm that has only the statement as an input. And we ask that the verifier does not know who he is interacting with. The standard indistinguishability notion, you know, verifier outputs a bit that says, I think I'm talking to the real prover, or yes. And this bit is output with almost the same probability if he talks to the real prover and if he talks to the simulator, except for negligible difference between the two. Fine. What does this capture? And this has to hold, and this has to hold this indistinguishability. It has to hold for all axes in the language and all within this W. So, you know, without loss of generality, that, for example, here, there might be many different randomnesses that explains the ciphertext. Okay. And in general, there might be more witnesses than one. It doesn't matter. It's very often this is moot. There is only one witness for a statement. Yes. Why would this capture an intuitive notion that the proof system does not leak information without W? Well, because if in the real world you're interacting with me who has the secret key and the randomness, but nevertheless you cannot distinguish this interaction from some efficient algorithm simulator who doesn't have any of these secrets inside him. So that means that anything as a verifier that you gain from this communication, everything that you output on the basis of this communication, well, the same thing you would be able to output when you just interact with the simulator, because the two are indistinguishable. And simulator has no more inputs than yourself. So this means that if you see the statement, you can run the simulator in your head. You can run this efficient sim algorithm on the side, right? And create the same view or indistinguishable view from the interaction with the real prover. Therefore, anything that, like in semantic notion of security of encryption, anything that you do, possibly you can do on the basis of seeing a ciphertext, if this definition is met, you can do on the basis of nothing. Meaning some things that you can create based on the public inputs. So therefore, any efficient algorithm out there who is listening to proofs, who is verifying proofs, cannot learn anything from them except that they exist in the language, because any generation of the proof is indistinguishable from a simulation of that proof. I'll give you an example of a zero-knowledge proof like this. So basically, this is how most zero-knowledge proofs go. So, for example, if you somehow believe that this object is unique, that there's no way I have two such objects, behind my back. And what I wanted to prove to you is that my right and left hand behind my back have no wall. I mean, that there is a connection behind me. You cannot see whether behind me is a wall. Let's say that you cannot see. But I will prove to you that this object is too big. This one, right? Let's say it's unique, right? So I'll prove to you that there is that my hands in the back I can connect, okay? Which you won't see, but you will be convinced. So now tell me whether you want me to open the right hand or the left. Left. Okay, so with 50%, I could have guessed that, right? And I was just lucky with the 50%. But otherwise, okay, so let's do it again, because perhaps I was just lucky, right? I placed this in a lucky way. And now, which hand? Right hand. Okay, so perhaps I was lucky again. Or, if I am able to, turn the hand, right? Right. Yes. So I was either lucky, with the probability 1 in 8 now, and if I continue doing this, it's probability 2 to the minus n, where n is the number of these attempts. So, if I do this 20 times, you're pretty much convinced, that because 2 to the minus 20 is 1 in a million chance that I could have guessed every time. So maybe you're convinced now that there is no border between my back that separates my left and right hand, right? Proofs are, and now, but have I really showed? So here is the thing. So instead of backing the hand, perhaps, if I had like a box with a key, I put a ball inside, and in the middle of the box, there is a latch door. I put this thing inside from one end. And you tell me, open it from the left or open it from the right, and I can, because I have the key that opens the latch box in the middle, and the ball can go left or right. You don't learn the key. You don't learn how to open, but you're convinced that I have the key that opens. If we can turn computational problems into these kind of, okay, either this or that, if both are true, then the secret key, then the witness must exist. But either, why is that proof 0 nor that? Well, because I don't show you the key, right? I don't show you how I exactly communicate behind my back. But more, if you think of yourself as an efficient algorithm, you're generating randomness, right? To ask for left or right. So every time you had one bit of randomness to decide. I could easily emulate that by basically guessing that bit, showing you either the left solution or the right solution, preparing the left or the right solution. And then if my guess is incorrect, then just backtrack the machine. You are a machine that has randomness, and based on that randomness, ask questions. If I'm unlucky guessing your randomness, I just backtrack you. I just rewind you a little bit. In the end, I will gonna produce random choices with solutions. And you, if you are a machine, you cannot tell that from the real trace of an execution. Let me give you a computational example. I don't know whether this works. But just well keep on doing it. So here is an example. The language is of graph isomorphisms. G0 and G1 such that there exists isomorphism phi that maps G0 to G1 in a one-to-one way. So you might have heard that two graphs, two complicated graphs, both of n nodes and roughly n square vertices. There is a hard problem to tell whether graph G0 is G1 is a permutation of graph G1. It's just some rearrangement of I take the nodes and I permute them, and I get graph G1. There is no efficient algorithms for verifying this. There are some heuristics you can run, like count the edges, or like count for every node, how many edges it has. So of course they have to have the same statistics. Okay, but let's say they do. You still don't know how to tell whether there is some permutation or not. There, of course, in exponential time, you can do all permutations, but that's n factorial, which is exponentially n. But say so the statement is two graphs, and let's say that the witness is the phi permutation. It's the permutation path. Here is how you can prove in zero knowledge that the two graphs are isomorphic without revealing anything about that isomorphism. The prover has the two graphs, that's a statement, and the isomorphism. The verifier has just the two graphs. The prover does this. It picks a random permutation pi. Think of the graph as just the permutation is on the nodes of the graph, right? Which once I permute the nodes, then I permute the edges correspondingly. And it sends a graph G prime, which is the permutation pi applied to G0. Let me draw a picture. G0 is permuted by phi into G1, and now he's permuted by pi into graph G prime. The verifier, when he sees this randomly permuted graph G prime, it asks a random question, which is like your question, left hand or right hand. It's a bit, and it's a random bit. And the left-hand answer and the right-hand answer that the prover will send are as follows. It sends a permutation, which I guess I can call pi b, which is defined as follows. It is pi if b is 0, and it is phi minus 1 composed with pi if b is 1, and finally d offsets if pi b applied to GP is this graph G prime. let's check correctness. So correctness is based on the following. Pi 0 will always be equal to this thing, to pi. And pi 1, sorry. No, I don't like to try. I'm going to call this thing G hat or G weight. So this G hat is pi 1 is this thing because this is phi minus 1 composed with pi. Right? How do I go from this graph to this graph? I invert this permutation and I apply this one. Okay. So this will verifier, when talking to a good prover who follows this protocol, will always accept. Two claims about this. Three claims. Number one, he always accepts when interacting with the prover. So if the prover, this is X and this is W. Right? The statement is the two graphs, the witness is the permutation between them. Okay. So that's just the correctness thing. Number two, and this probability is called soundness, and in this case, it's actually just 1/2 soundness, meaning that if X is not in the language, i.e. the two graphs are not isomorphic, i.e. G0 and G1 are not isomorphic, in this case, for this language, then V rejects with probability at least 1/2. So soundness is like our way of saying that you cannot convince other people of wrong stuff. So it's sound, as in I cannot introduce lies into the system. Like the system can only follow good stuff, and like lies are not going to be processed correctly. So the system will be sound in that way. Like it's not going to have, false things in it.
So like no false positives, but possibly false negatives.
Exactly. But 1/2 soundness is in some sense enough. Just like in this proof, there was 1/2 soundness. Perhaps I guessed with probably 1/2 that the hands that you're going to ask me for. But I just repeated a polynomial many times, and the soundness error goes exponentially down, right? So it's not super efficient because I have to repeat it 100 times for the soundness error to be 1 in 2 to the 100, which would be something that we would, really like in practice. But just bear with me because there is a way to actually make it completely practical. Okay? So let's start with this. Why does it have a 1/2 soundness? So this probability 2, why does this, why? Because if G0 is not isomorphic to G1, then okay, first, so how can I have better than 1/2 soundness? The only better than 1/2 is that I am able to give you the correct answer both for the question B0 and for the question B1. In the case of question B0, the left-hand side question, the 0-bit question, I have to surrender some isomorphism between G0 and G0. So the only way I can answer that possibility is that if this isomorphism exists. In other words, if G0 is isomorphic to G0. Likewise, for me to be able to give you an answer for question B equal 1, these two graphs have to be isomorphic. So if I have an answer, if an answer exists for both questions, then this is permutation, this is permutation. So this permutation exists. It's just these two composed, right? Permutation is invertible. So this one must exist. And conversely, if this one doesn't exist, then the only things that can exist is either that, or this, or none of them, right? Like if the prover is really dumb, then none of them exist, right? Because if there exists a permutation from G0 to G0 and G1 to G0, then there exists permutation G0 to G1. Right. So this is exactly this kind of binary left or right question. If both of them exist, then this means that there is no wall in the back of me. Right. And at every time you interact, you only learn about one of them. So you don't know that both exist at the same time, because you're only getting either the left permutation or the right one. You're never getting both at the same time. But the fact that I'm consistently able to answer this again and again, would mean that the probability that I'm managing without these two existing is 1/2 times to the power of however many times I do this. And so this is correctness, this is soundness, and here is the zero knowledge. It's zero knowledge. And finally, how do we ask you? Okay, well, here's how the simulator, given G0 and G1, can emulate these conversations. Guess B. Given that you guessed B, pick a random permutation in time B and send G0 as pi B applied to GB. If B gets correct, so if Z sends same B, you got same B, which same B, then sends back this permutation pi B. So the simple point is that if I guess B correctly, I have no witness. I do not know this permutation. I have no idea if the two graphs are isomorphic really. I know as much as you do. There are some two random graphs, and they have the same number of edges and vertices, but I don't know whether they're isomorphic. But I can still emulate this proof system, simulate this proof system by doing like as follows. I guess this bit B. And whatever D is, I either generate the hat as pi b of GB of so if b is 0, then I generated as a random permutation of T0, and if b is 1, I generated a random permutation of G1, and that's what I send here. And when the question from the verifier comes, if my guess was correct, I can answer this. And if V sends the wrong bit B, go back to step 1. Just start again. This is this is the most subtle point, because but the point is V is an algorithm. V is an algorithm that got X, which is the 2 grams, and he has a random tape as an input. Okay, so we can abstract randomized algorithms as that he has the real input and also some random tape from which he sources his randomized behavior, like these bits. What the simulator does is that he will sample basically these random tapes. He will the simulator on just the statement X, will perform this loop. Pick G hat as here, send it, pick B, send it, and recurse if B wrong. Why? Okay, maybe I can convince you that at the end result. So think of this. First of all, how long this procedure takes place? Is it efficient? Yes, because with probability 1/2 is I pass it. So what's the expected time? It's the expected time is 2. But even basically the probability that I never pass this after polynomial. Let's say I run it n times. I don't even stop. I just always run it n times. Okay, so this is the worst case. What's the probability that I never create a correct view? Is 2 to the minus n, because I have to be wrong every time in n attempts. So that's negligible difference. So if this simulator here ran n times, and he has a 2 to the minus n probability that he fails completely. He basically does not deliver a correct view. Well, so what's the distinguishing probability? 2 to the minus n. Because that event that the simulator completely fails is only 2 to the minus n chance. Okay, and then based on the assumptions that he guesses this bit correctly, is this simulated view different from the real view? And basically, they're not, because in the run where the simulator guessed. Well, the random bit was random, yes. How did these messages look like? This was a random permutation, yes. Note that, by the way, this in a real execution, pi b is always a random permutation, right? If in a bit 0, this pi was a random permutation. And if bit 1 is 1, then this is a composition of a random permutation with fixed 1. This is like a one-time pad on permutations. Fixed permutation composed with a random 1 is a random permutation. So pi b is always a random permutation. At least it's instructive to go backward. Fixed bit b, that's the bit b that resides here. And assume that the simulator guessed it. In a real execution, for that bit b, pi b is a random permutation, and g hat is a deterministic function of everything else, because g hat is just this value. So once pi b is fixed and bit b is fixed, then g hat is deterministic. So it's fixed by these two. Okay. So the view of the protocol looks, you can see it like this: a random bit, a random permutation, and this message, which is some which checks out for this bit and this permutation. It's a function. This graph is a function of the bit and the permutation, because that's what the verifier does. He verifies that it is that correct function of the final permutation that prover sends and the bit that the verifier chose. And what about simulation? It's exactly the same way. If this bit is bit correctly, then pi b is random by definition, and g hat is correct. So that's why simulated view is identical to the real view. They both contain a random bit b, random permutation, and in the last message, and the g hat that fits with the other two. This is a subtle concept, and you can. Here is an important thing to think through. If proof system can be simulated, then how come it's sound at all? How come a prover, a real prover who knows nothing, he does not know phi, in fact, G0 and G1 are not permuted correctly? How come that prover cannot do this emulation, this simulation? Right? I mean, this simulator really basically follows what I would call a cheating strategy. How would you cheat in this system? You would guess the bit. You have no idea whether G0 and G1 are isomorphic. Perhaps you even know that they aren't. So you're a real cheater. So you're guessing this bit. You pick permutation, and you hope to survive, right? So what distinguishes simulator from a cheater? Maybe, yeah. It's in front of this arrow that distinguishes the go back stuff. This is the thing that a simulator can do, because but a real world prover cannot do. I cannot, if you really challenge me, I cannot say, hey, let's stop time and let's go back in time. And I'm going to pick this bit again and do it. And if I'm not lucky, let's stop time and let's go back. There is no such thing in the real world, right? In a real interaction. But the distribution of this view can nevertheless be created by a machine that only has access and input. Let me show you a different form of different example of a zero knowledge proof that that is it's not a graph isomorphism, but it's about a problem that you have seen, like for example, a problem of Diffie-Hellman related to the Diffie-Hellman key exchange, and so, for example, it would allow us to prove this type of statements, this type of practical statements, like that. This encrypted thing is the same as the plain text here is the key over there, or well, there's many things we would like to prove. But you know, here is an example from a crypto system that you have seen. Let L be a language of Diffie-Hellman tuples. So GHYZ such that there exists a W such that G to the W is H, and sorry, G to the W is Y, and H to the W is Z. So this, in other words, the discrete logarithm between G and H is the same, G and Y is the same as the discrete logarithm between H and Z. This might not be obvious how from that I can go to proofs like that this Diffie-Hellman encryption encrypts the same thing as that one. But it won't be that far off. So let's show how that proof can work. So here the statement is this tuple of group elements, and the witness is W, and the verifier has just the statement, which is this tuple of group elements. The prover will now pick a random W prime at random in the order of the group. So this is order of the group. So these are all group elements. G, H, Y, Z are all elements of some group. And let's go the order of the group Q. So this is a modulus that works on these exponents. And he assigns values which I can call A, which is G to the W prime, and B, which is H to the W prime, to the verifier. The verifier now chose a challenge, which is no longer a bit, but actually it's a random value in CQ. And this will replies with the following: W prime plus the challenge times W mod Q. And the verifier accepts G to the Z is equal to that's G to the W, so that's A, times G to the W to the C, so that's supposed to be Y to the C, and a corresponding equation on H, so H to the Z would be H to W prime, which is B, and then H to CW, which is Z to the C. So you can see, this is correct because this is supposed to be G to the W times G to the W prime C, which is G to the W plus W prime C. sorry, actually, flip. And this is the same on H. So it's correct. It is actually one Q. So it's found with error much smaller, just 1 over Q. And Q is a very small number, right? Because these groups are of very large order. So why is that? If there exists for any AW, does not matter what he sends in the first round. If there exists C and C, let's say C0 or C1 and C2, they're different. Such that there exists Z0, Z1, which verifies, and Z2, which also verifies, namely, so what has to be for these to verify? So G to the Z1 and H to the Z1 must be equal to A, Y, C1, B, Z, C1. And also Z2 works. So G, Z2, H, Z2 is equal to A, Y to C2, B, Z to C2. In other words, if whatever prover says, if there is 2 challenges for which he can answer correctly both of them, remember, like the 2 challenges, B0 and B1, for which I can send correct answers, but now it's over the large group, Q elements, which is a large prime. Then it must follow the discrete log of G and Y is equal to discrete log of H and C. In other words, then for sure this is a correct thing. Okay, if there is 2 challenges for which I have a correct answer. So why is that? So let's see. I want to here sketch why 2 is true. So so look, from all these equations, G1 is A, Y, C1, and G2 is A, Y, C2. Then I just cross multiply them, I divide them one by another, and A drops out. So this follows that G to the delta Z, so C1 minus C2, is this divided by that, so A drops out. What I'm left with is Y to delta C. And if H to Z1 is B, Z C1, and H Z2 is B, Z to C1, sorry, I have C here, and as I call this response C. So I'm sorry. Yeah, okay, it's too late. But that's a different one. Okay, I don't know how to do it. Let's call him like this. So that's a C with a dash. Okay, then I divide this thing by this thing, and I get that H to the delta Z is equal D drops out to Z with a dash to the delta C. And from this, well, delta C is non-zero. So G to the delta Z divided by delta C is Y. And H to the delta Z divided by delta C is Z with a dash. So this is the W. Right? And assume prime because these operations are not Q. So exponents, they are negative mod Q. So that division there is a modular division mod Q, but Q is prime. So that's okay, right? Because you can divide mod prime as long as delta C is not zero. So it is very much like this system, right? If I can answer both the left question and the right question, then the statement must be true. Here, I don't have just left or right questions. I have the whole exponentially sized space of questions. And if I can answer any two, then the statement is right. So the error, in other words, the probability that I give you some wrong stuff and I'm able to prove it is just 1 over Q. Because it's just the probability that you happen to pick like some wrong challenge in a way. And that wrong challenge is precisely the cheating problem. So this is zero knowledge. It is zero knowledge technically for so-called honest verifier. What I mean by honest verifier, a machine that actually follows this algorithm. So it's really choosing a random C rather than choosing them somehow on the basis of these messages. It's a tricky little point, but that's a real thing. Like perhaps this challenge is somehow a function of the stuff, and then I don't have an argument. But in a second, I mean not a second, but hopefully 5 minutes, and I'll show you that that actually is enough for some very nice implementation of this. What does the simulator do if he only gets these group elements as inputs? So he doesn't know what these things are. You know, this could be basically it's like each pair is like an L-gamma ciphertext. Okay. And if they are encrypting, say, the same message, then the discrete log relations will hold in this way. But simulator doesn't know it, if they are or what they are, and he has no idea about the discrete log relations. So what can he do? Well, a very similar thing is here. Pick C at random. Compute it backwards. So pick Z as random. Set these values to be correct. You know what? I guess I'll erase this. Oh, maybe we should have photographed it because God knows whether this is watchable at all. Okay. Do it now. Oh, we can still photograph what's remains. So set A to be G to the C multiplied by Y to the minus C, and B to be H to the Z times Z dash to the minus C. note that once A and B are computed this way, then the verification equation is correct. So G to the Z is A to Y C, and A to the Z is B Z dash to the C, right? It's the same argument that this is the correct simulation. Because what happens if you are an honest verifier? So a verifier that really picks C at random. This is a random message. This is a random value in the queue. This is a random value in the queue. Because it's like a one-time tap. W exists if it's a correct statement. CW is some value, but W prime is completely at random, not Q. So this is a one-time path. W prime was computed, was random, right? So Z is a random value in CQ. And what about this thing? It's a function. Function of the statement GHYC, challenge C, and response C. And the function is this one. It's this function. It's this function. Because you see, if these AB values satisfy this relation, so that's if and only if A and B are this function of the statement GHY Z dash, the challenge C, and the response C. They're deterministic based on the rest. So what you see, what the verifier sees is that, well, it's a random challenge that he chose, a random response, and some stuff at the beginning which verifies. Well, that's exactly what he sees in the simulation. He sees a random challenge, a random response, and some stuff AB that verifies. So if you swallow that it's okay to produce this view backwards, just so that this distribution of the view is identical to the one that the verifier gets when interacting with the real prover, then this does happen here again. Except that this, it's only for the verifier that really does honestly chooses to see at random. If the C is some weird function of this stuff, then we are getting into a loop. Let me try to photograph this for if there's anyone who who tries to follow, not really not really sure about the quality of this video. Okay. So here is a very popular implementation of a zero-knowledge proof for which this assumption suffices. And moreover, they also they have a very sweet additional property. If H is a random oracle hash, So if we believe that phi is like a random function, okay, then this leads to non-interactive zero knowledge proof, so-called basic. So this non-interactive proof, I'll just give you for example of this. So again, the language is of it's the same language of correctly formed Diffie-Hellman tuples. So the discrete overtures between G and Y and H and Z hash are correct. The prover who has this statement and a witness for it follows this. So in other words, he takes W prime at random as a random Q, computes AB, which is G to the W prime and H to W prime. And then he locally computes the challenge as a hash function of everything that was seen before. So the statement and this first message that he would normally send if it was an interactive process. And then he locally computes the response, just like here. So this was W prime plus CW mod Q. And outputs a single bit string, let's call it pi, composed of Z and C as a proof for the fact that this is a correct Diffie-Hellman tuple. Let's check how the verifier operates. So verifier given the statement and the proof, which is C and Z. That's the following. He emulates this proof sort of backwards. So he computes A and B as values that would verify. So G to the Z Y to minus C and H to the Z hat Z dash to the minus C. And accepts if we only if C is the hash of the proper stuff, which was the statement, and this presumed first message. How does this non-interactive system differ from the interactive one? Actually, not much, because you can reverse this procedure. You can say AB is equal to that stuff. You can just put AB on this side and just stuff on that side, right? It's the same equation. So the only difference is that instead of this being chosen as in this way, both parties set C to be a hash of the statement and this presumed first message of the prover. The prover sends this first message in his head, computes the challenge based on this and a response, and actually does not send this message. It's actually, by the way, long because these are group elements and these are short. So it's even better. You don't have to send this. It can be recomputed by the verifier. So you just output these two as the proof. The verifier computes this first message that would fit and checks that the challenge is computed correctly. Now, why is it okay? Because if you believe H is a random oracle, then neither party could have manipulated it. So basically, if you're getting this kind of stuff non-interactively, What is it that verifier loses? He loses control over C. He is not, in an interactive system, where is his soundness comes from? It comes from the fact that he chose this at random. So if the statement was wrong, the probability that this is chosen wrong is very low. It's 1 over Q. But he chose it at random, so he knows that's unlikely, right? But he surrenders his randomness to this random oracle. But it's a random oracle. So the value is random. We just trust SHA to compute this challenge for us, given a statement and the first message, we just delegate to SHA, like, dear SHA, tell us what is the challenge for this statement and what challenge would you pick? And he picks a random one because we believe that it's a random function. So in this weird world where, like, we believe that some deterministic SHA, whose code everybody knows, is a real random function, yes, it's okay to delegate this action. So therefore, this can be pre-computed on the prover side, and therefore the short bit strength CC can function as a non-interactive proof. It can be said, I can give it to you, and now, unlike an interactive proof, where if I prove something to you, you cannot turn around and prove it to others. In a non-interactive one, I give you this, you can show it to others, which is really good for blockchain stuff. I prove something once, and now this proof can go around from one node to another, can bifurcate through the network, be broadcasted, and everybody can verify all transactions by checking these non-interactive zero-knowledge proofs. And conversely, for the prover, what was it that he lost by not having the control over, okay, so is it okay for the prover that the challenge is chosen by this SHA? The only place where it could have any tolerance is zero knowledge. Is it, what the simulator kind of forgoes is this choice. But that's okay, because if this random function is truly random, then the simulator basically will, it's like, you can think of this simulator as, efficient attacker. He can query the random function, but it's a random function. So a simulator can basically manipulate the random function too, and can embed the C that it wants in the view, in the response. So an interaction with such a manipulated random function is indistinguishable from an interaction with random function, because this C is still random. This hash value is still random. It's just manipulated by the simulator who takes this value, computes this, and then manipulates the hash function, namely declares that the value of the hash function on this input is the C that the simulator chose. But because the simulator chose it at random, such view is indistinguishable from a true random function. It's still, this value is still random. It's just chosen by the simulator in this procedure. I will, sorry, you don't want to hear this, but I might add to the final exam runner, like because so you have shown that we have shown the non-interactive proof for discrete algorithm, and so what? So can I use it now to say prove that two ciphertexts encrypt the same value? And this is like a nice little exercise. Actually, you should look at what that means for Diffie-Hellman encryption, and you will see that you can cast it in this form. So what I just showed you, is actually could be used to prove some realistic proof systems, useful statements already. Okay. Thanks. Okay, you should kill this thing. Oh, we do have 3 people. Hi. But see you Thursday.